Alright, so this video is going to talk about doing heatbox control with the Beaglebone. So the first topic I want to talk about is pulse width modulation, and then we're going to look at fuzzy logic control and a dual BJT interfacing circuit. So pulse width modulation allows us to simulate an analog output value by pulsing the DC constant value. This is useful because it reduces power switching and losses. We can mimic sine waves or other waveforms for it, and there are actually certain types of servos that require a pulse width modulated input to control the servo. So this is a pulse width modulated waveform here. And this one here is just a simple on or off, but it has what we call a duty cycle. So the duty cycle is the amount of time that it is high, and then the period is how often this is repeated. So this may be repeated once every millisecond or once every 2 milliseconds or so on, depending on your setup here. So we have the frequency is 1 over the period. So the period is how long it takes. So if it's like 1 millisecond, the frequency would be 1000 hertz. And then the duty cycle can go anywhere from 0, which means that actually it's just a constant 0 out, to 100%, which means it's at the high all the time. Now remember, this is what we're doing is we have a DC value, so it's an unchanging value, but we're switching that and allowing that DC voltage through or not. And so the actual magnitude of this just depends on the size of your DC voltage. All right, so as I just said, 0 means that the output will just be off all the time. 50% means that you're going to have, it'll be on for half of the cycle and off for the other half of the cycle. Now the Beaglebone that we've been using for some of the labs in class supports pulse width modulation. Now just in general, it doesn't have to be the Beaglebone. You can do pulse width modulation through software. So you can run a software program, and with that software program you can just output a 1 and then use a timer or counts or something, and then put a 0 out. We could have done that with our PLC using something as simple as a timer and something like that, and just outputting, and we could adjust the width of it by changing the time of our timer. So you can do that with any kind of software. You can do software, but the Beaglebone Black and a lot of other microcontrollers and or dedicated kind of controllers actually have what they call hardware dedicated circuitry on their I/O chips, and with this you get a very consistent waveform. So all you have to do is you set it up, you tell it what your frequency or your period is supposed to be depending on the setup, and then you tell it what the duty cycle is, and then anytime you want to change a duty cycle you just write out the new duty cycle. So with the Beaglebone Black, you could, if you look at the pinout, which I've showed you that before, so this is just a small portion of the pinout showing P9, but if you see this where it says PWM, and there's like several pins there, but any one of them listed as PWM are possible ones that you could use for a hardware pulse width modulation. Again, any GPIO could be set up to be a software, but these ones actually have built-in circuitry to do hardware PWM for that consistency. Now the way these work inside of the Node-RED software then is that it's an 8-bit control to control the duty cycle. So 8 bits means 2 to the 8th gives you a maximum of 255. So your range is 0 to 255. So if you output a 255, it would be on all the time. Alright, so here is the GPIO output node. We've used a couple of these, but there's these settings here, so you can see the settings. One of the settings is analog. So if you select analog, then you can see it gives you that range from 0 to 255. You could also select servo. The servo will send out a dedicated pulse for, as I mentioned before, dedicated servos that are looking for this. I believe it's a 50 millisecond period, and then the duty cycle could range from 0 to 180 if you chose the servo. But for us, we'll just use the analog, which is a little more straightforward, and it gives us a little bit more control from 0 to 255. So when you set an analog pin, you need to make sure you select one of these hardware analog pins to use this particular feature, and then you set whichever pin that you're going to be. Remember, it needs to be a capital P, and then 9 or 8, depending on which one you're using, an underscore to set that, and you can send that out there. Alright, so now I wanted to introduce something called fuzzy logic control. Fuzzy logic allows us to control complex systems, or they can be simpler systems, but the cool thing is, number one, it could be a very complex system we don't understand very well, but we can kind of describe in general terms what we would like it to do, and then we can build our control system around that, so we don't need precision values. Now, this was first actually introduced in 1965 in a paper called Fuzzy Sets, and it's actually a form of artificial intelligence. Alright, so the main concept of fuzzy logic control is that we can apply what they call reasoning or vague terms or fuzzy terms. So instead of saying something like, oh, I have a nice crisp value of, say, 97.8 degrees Fahrenheit, we can use terms like warm or cool or hot. Okay, so binary logic, which we've dealt with before, right, is just it's either a 0 or 1, on or off, true or false. And again, our DC, our output, we're only going to put out a high or a low, but we're going to vary the time of that. And so the fuzzy logic applies degrees of truth. So instead of saying, it's either true or false, we can put in degrees and say, well, it's 0.8 or 0.7 or something like that. So the fuzzy logic process here, we're going to usually, now again, everything in here, we're just kind of, I'm not saying that this is the only way you can do fuzzy logic. I'm just saying, this is a very common way, and basically what we're going to do. So we're going to take a crisp input value or a finite input value, like 97.8 degrees or something like that. And that's going to be our input. And we're going to use the heat box, so it's going to be, a temperature value. So we're going to say, well, if the temperature is hot, then we do this. If the temperature is cold, then we do this other thing. And so we have these fuzzy sets: hot, cold, warm, lukewarm, whatever you wanted to call them. And then we read in this crisp value, we run it through the fuzzy set and see where it falls within the fuzzy set, and then we defuzzify back into a crisp value. Typo there, I see that. Into a crisp value, and then we can output a response based on that. So for us, we're going to output our duty cycle as a crisp value. Alright, so just a term here. So the fuzzy logic uses linguistic variables. So when we're talking about these, say, fuzzy sets here or whatever, we're talking about freezing or cold or cool or warm or hot or melting. So they're linguistic terms, right? Terms that we use when we're talking, and so again, they don't necessarily have a numeric value to them. Although the way that we will set this up, they will kind of have a numeric value. So let's look at an example here. So this is an example. I just have three temperatures. I have a cold, a warm, and a hot. And so the blue here is cold. So what I'm saying is anything below 90 degrees is 100% cold. And anything above 105 degrees is not cold. And so then this range from basically 90 to 105 degrees is a variation of cold. So it's a variation or a degree of cold. And then the green is warm. So here you can see that it's warm at exactly 105 degrees. So at 90, it's just starting to turn warm, and then we have this degree of warmth between 90 and 105, and then it drops back off here. Now when you set up fuzzy sets like this, you can use nice straight lines that make like triangles or trapezoids, or you could use, if you really wanted to, you could use some kind of curved thing, like usually they refer to it as a Gaussian curve or something, like a nice smooth curve. However, when you're going to implement this inside of a computer, especially a small microcontroller type computer, you really want to implement this with straight lines, just because the amount of compute effort is very, very simple. So let's take a look here. I have 3 points kind of marked on here. So point A up here is about 90-95% cold. And so if you look at this, then you're going to say, well, what are you going to do when it's cold? Well, you're going to turn the heater on full blast so that you get hot, that you warm it up very, very quickly. All right, so remember, again, we're using this heat box. It has those power resistors that are heaters, basically a heater inside there, and then we have the fan system. Now, if we look at B, at point B here, it's like, well, it's about, say, 50% cold, about 50% warm. So what you're going to do then is you're going to be like, well, we don't necessarily want the heater on full blast at this point. We still want the heater on, but not full blast. And so what we can do is we can average this and come up with like a duty cycle. So up here at, like, say A, or to the left of point A, we would want to turn on that duty cycle so that the heater was on all the time and the fan was not on at all. All right, so we'd have a 255 duty cycle for the heater and a 0 duty cycle for the fan. But here at point B now, it's like, well, we're still cold, to say, because basically we're looking at this pattern that we're kind of saying that 105 is where we want the heat box to be. And so we're not quite there, so we probably don't want the fan on at all, but we want the heater on, but we maybe don't want the heater on full blast now. We just want to kind of, we're getting warmer, and so we don't want to just overheat it. So we maybe turn it on with a duty cycle of, say, instead of 255, maybe 230 or 200 or 180. All right, and this is what we get into called tuning. I didn't put that in the slides, but you have to tune your fuzzy sets to get the system to behave the way you want. And in this case, I only have 3 of these sets, cold, warm, and hot. But we could add 2 more or 5 more, or as many as you feel you need, and then you can tune the system by adjusting basically where these lines cross in here. And then if we look at point C over here, we say, well, point C, we're basically at about 80% of hot, and so that leaves about 20% in this particular case warm. And so it's like, well, it's like we're getting on the warmer side. We're not 100% hot yet, but we're getting pretty close. So we want to turn that fan on maybe quite a bit. Okay? And so, and we probably maybe want to turn the heater down or turn the heater off depending on what you need. Now with the heat box that we're using, it seems like you may not want to turn the heat off all the way, because that fan really blows the heat out of there quickly. So you probably don't want to turn the fan on 100%, maybe 50%, unless you're like way over here. And again, that's where you could add another set, another fuzzy set here, where you're like very hot or something. So at very hot, you probably want to turn it on 100%. But at hot, I would say no more than 50% for the fan. All right, the other thing that we're going to do to power the heat box, we have those power MOSFETs in there, and they need about 20 or more volts on the gate to actually turn them on. So we can't power those with our Beaglebone, which only outputs 3.3 volts. So what I have here is a picture of a PNP NPN transistor set here. So I have Q1 and Q2. These are a 3904 and a 3906 paired set of transistors and wired up so that when you activate the NPN transistor Q1, that's going to turn on, that's going to feed this resistor and feed current into the base of Q2, which is actually going to, this is a PNP transistor. We don't use those as much, but remember, these are backwards. So this is actually going to pull the MOSFET up to 24 volts, okay? So we have the blue wire here is to the collector of the Q2, the PNP transistor. So that, and then that one now is feeding out to the MOSFET inside the heat box to activate that. Now this pull-up resistor here is coming down to the base of Q2. And this is just to, when you shut off Q1, you want to make sure that Q2 also shuts off very quickly. And so you have this pull-up resistor to help pull the base of Q2 back up. But the blue wire is the one running out to the MOSFET. So this blue wire down here is the 3.3 volt output pin coming from our Beaglebone. So we have 3.3 volts here, which activates this transistor, and then it activates this transistor, pulling the MOSFET high up to 24 volts. Now I also have this LED here. So we have this resistor here. I think it's a 680 ohm resistor in series with an LED, and this is simply to give us a visual so we can see when this transistor is on or not. Okay, so there's 24 volts up here. Okay, so that is actually a 6.8K. That's red. That's a red stripe on there. So it's a 6.8K, not a 680K. So for 24 volts, 680 is going to allow way too much current to flow through there. So we need to be careful of that. Okay, so again, it's a 6.8K resistor. All right, so those are our topics for the week: pulse width modulation, fuzzy logic, and this push-pull transistor circuit.